All right, so I'm going to be writing a lot or drawing a lot of these distributions. First, we're just going to look at the distribution of the sample mean. All right, so just putting a little X bar over to the side, so this, we know that this is the sample, the distribution of the sample mean. Guess it wouldn't hurt to write that above it as well. All right, we know that the mean of the sample means is mu, right? The population mean for our random variable X. We know this because the sample mean is unbiased, right? So the expected value of the sample mean is also the mean of the sample mean equals mu. So that is our sample. So that's what we're trying to contain in our interval. So what we're going to try to do is we're going to try to create an upper boundary and a lower boundary, so that with some measure of confidence we can assume that the population mean falls between these two values, right? So what we're doing ultimately is we're trying to find a way to get numbers for the upper boundary and the lower boundary. As we have seen with our negative infinity to positive infinity interval, a interval that goes out forever is not very helpful. We're going to have some way of defining how small we want that interval to be, or or some way of gauging how far out to take it. All right, the way we're going to do that is by defining a probability with which we want the mean, the population mean, to fall in our interval. Right, we're going to notate that probability as 1 minus alpha. So alpha has to be between 0 and 1. So we're going to get a decimal value. We're going to get an actual probability. Right, this 1 minus alpha, your book calls it the confidence coefficient. You may hear it referred to that. I don't really ever hear it referred to as that. But what it does give you is it allows you to find your confidence level. So 100 times 1 minus alpha percent, that's your confidence level. And so you can kind of reverse engineer that, right? Whatever the percentage is, your confidence level, 1 minus alpha is just moving the decimal places over a couple spots to make it a decimal value instead of a whole number. All right, but that is our confidence level. We're going to talk a little bit more about that in a moment. All right, so now we're going to move on to the next step. We know that the distribution is approximately normal once that central limit theorem kicks in. We also know that this means we can standardize our sample means, right? And by definition, this upper and lower bound falling on here, these would be kind of examples of the sample mean. We can treat them as a sample mean. So we can standardize the upper and lower boundary. Now that we're standardizing, we're no longer looking at the distribution for the sample mean. Instead, now we're looking at the Z distribution. So our upper boundary would be here, and if we don't recall, our standardization or our Z-score formula for the sample mean is x bar minus mu divided by the standard deviation divided by the square root of n. In this case, UB, the upper boundary, is going to take the place of our x bar. We're going to subtract that mean, and then we're going to divide by sigma divided by the square root of n. We're going to do this process again for our lower boundary. So the only thing changing here is that we're using LB instead of UB, and we are maintaining this 1 minus alpha, right? This area under the curve between our upper and lower bound, that is going to be 1 minus alpha. All right, now I'm going to change this once again. Right, because, well, actually, before I do that, so when we look at this, we can see that, right, the area under the curve between these two is equal to 1 minus alpha. So that must mean that the area under the curve, right, outside of that is equal to alpha. And these are going to be equidistant from the mean. That's the goal. So the area under the curve is going to be equal for these two, the area in the tails, right? So looking at this area, right? So this red area, actually, just to make this a little bit more clear, we'll do this. All right, so our red area and our blue area added together equals alpha, right? It's the remainder once we take the middle section out. So these are together equal alpha. There are two of them, so if we're looking just at the red section, this red section, the area under the curve that's shaded in red, is equal to alpha divided by 2. So why is this important? The reason this is going to be important is this is what's really going to kick off and allow us to start getting some answers. So I'm just going to erase those real quick. I wouldn't erase them on your page. I would just pause, redraw the graph, and then follow along. So I'm not even going to, well, we'll write that one down in a second. So what we have with our standardized values, right? Our standardized upper bound, our standardized lower bound, they are going to be tied to a z-score, right? If we had actual numbers and we were able to plug them in, we would get a specific value, we would get a specific z-score. We're going to notate the z-score, right, that's sitting here for our our lower bound as z alpha divided by 2. Right? The reason what this means well, that got a little cramped. We will write it down here. Right, whatever the subscript is on our z, that is telling us that's the probability that a randomly selected z would be less than that. Right, so the probability that z, right, our random variable as a whole, is less than or equal to this value equals alpha divided by 2. Right, which makes sense because what this is asking for is the area under the curve to the left of that value. That's what we've got shaded in. So if that is the case, then we can define, right, or pick an alpha that we want to use. Right, that would allow us to find a z-score, and that would allow us to solve for that lower boundary. Right, so again, that Z alpha divided by 2 and the standardized value for our lower bound are equivalent, they are equal. So this is the formula, right? These are equivalent. So if we want, we can solve for that lower bound, right? What we'll do is we'll multiply both sides by sigma divided by the square root of n. And then we will add mu to both sides, right? And I'm going to do a little rearranging so that we have the left bound over here. But really, again, we're just adding mu to both sides, so it cancels out here. We've got all of this plus mu. And then we can rearrange things a little bit. And we'll see that our lower boundary is equal to mu plus Z alpha divided by 2 times sigma divided by the square root of n. Right, now, since our distribution is symmetrical, we can find the upper boundary easily as well. All right. There are going to be some things. We could also derive it, but we don't necessarily need to do that. One thing I will note. When we go to find that upper boundary, there are some changes in the way that we're going to notate this. Well, actually, we'll just look. So, if we're looking at what we have, right? We've got this Z, right, that's tied to our upper bound. The area to the left of it is what would be the subscript. So in this case, it would be 1 minus alpha divided by 2. All right, however, we know that this is symmetrical, so we could also just say it's the negative value of Z alpha divided by 2. All right, negative Z alpha divided by 2. So when we do that and we do some rearranging, or really we're just saying Z 1 minus alpha divided by 2 is equivalent to Z alpha divided by 2 negative, so we can just make that negative. All right, it's going to give us that upper boundary. All right, so this is our lower and upper boundary, and a lot of times it's going to be written all together. Mu plus or minus Z alpha divided by 2 times sigma over the square root of n. So this is our interval. This is what we've been looking for, right? We're not quite done, but we're very close. So the big thing with this is we're trying to estimate the population mean. We're trying to get an interval estimate for the population mean. So it doesn't make much sense for us to have the population mean in this formula. Right, so instead we're going to estimate the population mean with the sample mean, right? That's what we're doing. That's why we need to know kind of what our error is. So once we do that, now we have our interval estimator. And this particular interval estimator is called the confidence interval. So this is our confidence interval for the population mean, or more specifically, the 100 times 1 minus alpha percent confidence interval for mean. X bar plus or minus z alpha divided by 2 times sigma divided by the square root of n. So this is going to give us two values. It's going to give us this interval. And it's going to give us, right, so as it is right now in the formula, as a formula, right, the probability that the population mean falls into an interval using this formula is that 1 minus alpha, right? That's the probability, right? So to clarify that a little bit, let's actually talk about alpha and talk about specifying alpha, right? Because we're going to have to do that to be able to work these problems. All right, so suppose we set one minus alpha to, let's say, so 1 minus alpha, that's going to give us the probability that our population mean is in our interval. Let's go with 95%, right? So 1 minus alpha would be 0.95. So again, if 1 minus alpha is equal to 0.95, then we're looking at a 95% confidence level. All right, so again, you see that 1 minus alpha times 100, 95, and then you add the percentage, 95%. So, if I get my pages, there we go. Right, and once we've got our alpha, then we can get that alpha divided by 2, or z alpha divided by 2. So we got a 95% confidence level. 1 minus alpha is 0.95. So the interval that or the estimator that we create for this, for a 95% confidence interval, the probability, the population, excuse me, let me take that again. The probability that the population mean falls into the interval as we're about to define it is 0.95. That is the probability. So let's look at finding that z. All right, so if 1 minus alpha equals 0.95, all right, we can do some simple math to determine that alpha is equal to 0.05. All right, now we know that we need to find this z alpha divided by 2, right? We know that the probability z is less than or equal to z alpha divided by 2 equals alpha divided by 2. So we need to find the z-score, right, where the probability that a randomly selected z is less than it is 0.025. All right, so to do this, we could go to our standard normal distribution chart. We can look around in the probability, so in the middle part, not around the edges, but in the middle where the probabilities are. We'll look around in there until we find the probability 0.0250. Then we'll follow that out to the sides, and we're going to see that negative 1.96 is our z alpha divided by 2. All right, so the probability z is less than or equal to negative 1.96 is equal to 0.0250. So that is our z. now that we have that, we can specify this 95% confidence interval. As x bar plus or minus 1.96 times sigma divided by the square root of n. All right, you may have noticed that I dropped that negative off of the 1.96. The reason for this is because we're adding and subtracting it. So if we did negative 1.96 or positive 1.96, it's not going to make a difference. We're going to get two answers and they're going to be the same either way we do that. I drop it off just because one, it's kind of standard, and also you don't really need that negative hanging around. There's no point to it when you're going to get the same answer either way. All right, but that is our 95% confidence interval. All right, again, we can interpret this a confidence interval made using this formula has a probability of 0.95 of having the population mean fall in that interval. All right, before we actually look at an example, let's talk about some common alphas, some common confidence intervals. So this isn't really kind of the wild, wild west. You're not going to be picking just whatever confidence level you want. Technically, I guess you could, but there are 3 standard confidence levels. All right, we've got 90%, 95%, and 99%. So as you might expect, the further down we go, the stronger our results are, right? If I'm 90% sure of something, then I'm not as certain of it as if I'm 99% sure, right? So as we go down, we're getting better results, really, more precise results. Or well, take that back, stronger results, right? Stronger results. As we go down, we also widen our confidence interval, as we're gonna kind of see. We're gonna see why here in just a moment. But we're gonna widen that confidence interval. So we are getting a wider confidence interval, but a stronger result. All right, these are also tied to specific z alpha divided by 2s. All right, so these are z alpha divided by 2. This is what we're gonna call the critical value. We'll get more into that in the next chapter, assuming we get to it. But if you're in the spring 2020 semester, we may or may not get to it, we'll see. All right, but our z's, we could find them just like we did our z for 95%. So I'll go ahead and write that up there. It's 1.960. However, for the 90 and 99%, the probabilities aren't actually on that table. You have to kind of get in the middle of them. So I'm just going to go ahead and tell them to you. So for 95 or for 90%, the z-score, the critical value, is going to be 1.645. And for the 99%, our critical value is going to be 2.576. All right, so now we can probably see why increasing the confidence level is going to increase the width of our interval estimate, because we're multiplying these numbers by what these numbers are part of what we add and subtract from that sample mean. So if these numbers get bigger, that whole portion gets bigger, right, and makes the interval wider, right? So these are our common critical values, right? They're associated, or excuse me, our common confidence levels, their associated critical values. And I'm also going to just pop up the alphas that correspond as well, just so we see those, because sometimes you'll be given that information as alpha or as the confidence level. Right, so for the 90% level, our alpha is 0.1, for 95 it's 0.05, and for 99 it's 0.01.